It's a great pleasure to visit KAUST. I've heard so much about this place, never been here. Yeah, so finally I made it. And I actually noticed earlier today that kind of half of this talk I've already given in the seminar. So the first half will be very boring for all of you because you clearly remember every word that I said during my last talk. So this will be a bit of a recap in the beginning, but it will lead very naturally to the second part. So the first part, which is optimization, second part, which is sampling. And so I'm fairly proud of this work, I think, because I this was the first COVID paper. This second paper was my first COVID paper, I think 2 months into lockdown. And that's came out I think like 2 years ago, and we've kind of done some follow-up work on this, actually quite a bit of follow-up work on this, and some very recent follow-up work which kind of transfers all of this the stochastic gradient descent business, or this stochastic gradient descent continuous time, I didn't even mention the title yet, business into Markov Monte Carlo sampling, and that's what I want to talk to you about today. So first we have some motivation. Okay, so why even do stochastic gradient descent? So the title is subsampling in continuous time, and okay, so why would you subsample? Why would we do this in optimization? Why would we do this in like Monte Carlo sampling? Then why is it difficult? So what can go wrong when we're doing this? And how can we analyze this? And I think this talk will be mostly about some new ideas how to understand subsampling algorithms that are very popularly used in especially machine learning-ish applications, but very badly understood, whilst being very popular, actually being fairly badly understood when being used. So let's see whether we can learn something new about this. So throughout this talk, we will always consider some potential or kind of energy functional that looks like this, so some phi bar that is given as the mean of some functions phi I. And we always have this, given as a function on some space x, that will always be r to the d. I think many of the results here will be easily transferable to infinite dimensional settings, but it's not the focus today. Yeah, I mean, could do that some other day. And now, given such a functional, we always say, okay, it's at least continuously differentiable. We later need some more assumptions on it, but for now, it's continuously differentiable. We're interested in two different problems. The first one is find the minimizer of the functional, find the minimizer of phi bar. And the second one is generate samples, θ1 up to θn, from distribution pi, where pi is given as the measure with the potential of phi. So the density of phi, the Lebesgue density of phi, is proportional to e to the minus phi bar. And kind of always I use like density and measure kind of equivalently here because it will always be Lebesgue densities, and so that's like broadly fine to do that. Okay, where do these problems appear? Okay, optimization, especially in machine learning or imaging statistics, and where these phi i's probably refer to single data sets, or to single pixels in an image, and I may have many of those. And one of them may actually be a regularizer that I then have to care about as well. In sampling, of course, these phi i's are kind of like log likelihoods, or something like this, and I want to sample a posterior. So pi would be a posterior, and e to the sum of these phi i's would then be many pieces of my log likelihoods plus a log prior, something like this, or minus negative log likelihoods and negative log prior. And I can also find problems like this in statistical physics, but I'm not a physicist, so I wouldn't know much about that. Now the problem is that most classical techniques are very expensive when n, the number of data sets, is very large. We'll come to that in a moment. And the idea is, or the idea that many people are using in these settings is use so-called data subsampling. That is, instead of having all n at the same time, I have only a few at the same time, or only one data set at the same time, and not all of them. Okay? So in machine learning, kind of n could be 35 million. If it's pictures of cats and dogs, it could be a huge number that I want to train my neural network with, or something like this. And then, okay, I cannot do all it at once. So I pick only one cat photo at a time or one dog photo at a time. And I learn just track to this. Yeah, so I use my algorithm, I apply my algorithm at a time just to one data set. Okay, now what can go wrong when doing this? So when doing this in stochastic gradient descent, what happens is I get an algorithm that I can use suddenly. Yeah, but gradient descent would be too expensive, but the algorithm that becomes quite inefficient. As the convergence rate is only like 1/square root of k, so it's not particularly fast. I can do variance reduction sometimes. That's quite popular nowadays. But if I'm very high dimensional, probably I can't because I would need to store more things, and then yeah, that's kind of difficult. The other thing that people use this for is because actually it introduces some error that is wanted, which is kind of separate from like what I said previously. Okay, we want to find a minimizer, and that's difficult with this method. But kind of the kind in which it's going wrong, what this method does, what is going wrong, is actually kind of wanted, because the problems I'm solving may not actually be like nicely convex conversation problems, but they may actually be much more complicated. And therefore, I might actually like this additional noise coming from SGD. And I call this implicit regularization, maybe, which may even help stopping my neural network from overfitting or something like this. Yeah, okay, so this kind of weirdly defined or not well-defined structure around stochastic gradient descent also contains actually finding something different than the optimum and actually liking what I find rather than the optimum, but not being able to describe it correctly. Yeah, so that's kind of like a subordinate goal when doing stochastic optimization is, or research on stochastic optimization is to actually figure out, okay, does it converge and what does it converge to? And why is what it converges to better than what it's supposed to converge to? Okay. Yeah, so the question obviously is, okay, can we do better? Yeah, so can we understand what happens when I use stochastic optimization to regularize my problem? And also, can I get more efficient algorithms, maybe without using variance reduction techniques? In sampling, subsum is actually quite difficult. Yeah, so there are some accurate subsum strategies. Yeah, like this paper by Berkens, which uses PDMPs. Yeah, piecewise deterministic Markov processes. It's a fascinating technique, but it's really hard to apply in practice. So this would be absolutely accurate, but it's very hard to apply in practice. The problem of inaccurate methodology is that it's usually not very efficient, and we'll come back to that in a moment. But that's of course also possible. Yeah, if you just say, okay, I just subsample in my MCMC algorithm, I will just get like a wrong result, and I might be wrong and quite far away from what I want to have. Yeah, so it's non-trivial. Okay, and also can we do better there? Okay, so in this talk, we will look at continuous time formulations of these algorithms, which is kind of a bit awkward because continuous time and kind of algorithms are discrete in time. Yeah, so I need something I can iterate over. But continuous time formulations make the analysis much easier, or sometimes much easier, because they're actually certain things that I may see when analyzing algorithms in discrete time that I don't care about particularly. I'll come to an example in just a moment. But for this talk, we want to figure out, okay, what happens if I reformulate stochastic gradient descent that I just talked about in continuous time. I want to know, okay, what happens with this implicit regularization? Okay, we'll talk about that in a moment. When we say, okay, actually what we see is it does not always converge to a point, but when I use it incorrectly, it converges to a stationary measure, which might tell me something about the implicit regularization that it does. Yeah, because suddenly I don't converge to a minimizer, but I converge to some broader class of things, which actually explain, or which might be more robust in certain settings. Yeah, I mean, and that's, I think, what the machine learners want. The long-term goals here would be to actually figure out, okay, what is this measure in particular, which we don't see here. Here we just know, okay, we quickly go somewhere, but we don't actually know how to specify this. But that, I think, is something that is fairly important in the machine learning world. And we come back to that, how this looks like in particular in just a moment. In Stochastic Gradient Langevin Dynamics, which is the sampling bit, it's an inaccurate sampling technique that essentially just using some classical MCMC method called Euler, unadjusted Langevin algorithm, and subsample within those. And here we want to figure out what is actually the subsampling error just by doing that. So there's two errors. There's one error from the unadjusting Langevin algorithm. We understand this. We don't care about that. We only care about subsampling. And here, of course, we want to find more efficient subsampling-based MCMC methods. Okay, and this is a slide I thought was the last slide. So why do we do things in continuous time? And the answer is, when we do things in discrete time, we may see effects that we don't really care about or that we think that we understand already. So if we say, okay, what stochastic gradient descent to some extent does, or what some optimizers to some extent do, is they just solve very stiff ODEs. And solving stiff ODEs like gradient descent essentially is solver for a stiff ODE, and the stiff ODE is a gradient flow. And stiff ODEs are difficult to discretize. So we need good techniques for that, but we know how to do that. And so when I say, okay, I want to know why stochastic gradient descent is so inefficient, I'm not sure. Is it inefficient because I'm sampling, or is it inefficient because I use forward Euler for a stiff ODE? And therefore, by saying, okay, let's just forget about the stiff ODE for a moment. Let's just focus on the subsampling. We may actually get more interesting analytical results later that tell us something that what is inherently wrong about SGD, that is not connected to just numerical analysis of ODEs, because that we understand already. Okay, and it's not like we came up with any of this. I mean, there's a whole zoo of things, especially in the machine learning world, that are now analyzed in continuous time or continuous space settings. Just because that makes certain things much easier. But I mean, also, okay, I say recently, there's like the famous paper by Rudolf Fatemi in 1992, where people solve a PDE to reconstruct an image. So this has been around for quite a long time. Of course, when we will see, we will always get like excellent convergence rates. Of course, those don't really translate from continuous to discrete time. That's like a problem for another day. Or that's almost what I've been saying that for 3 years now, that I will do this another day. I might wait like 2 or 3 more years to do it, but that is something to always keep in mind. Okay. Sorry, I think this part of talk was overly confusing. I promise it will get less confusing on the next 80 slides or so in the next 3 hours. Is that what I have? Okay. Are there questions up to now? Okay. Okay. So just back to discrete time for just a second. So how do we solve this optimization problem? So we said these phi i's are continuously differentiable. So what we can do is we just do gradient descent. Okay, gradient descent just means from my current position where I'm now, I just do one step in negative gradient direction. Okay. So just theta k minus some step size eta k minus the gradient of phi bar. Of course, the gradient of phi bar I can get as the mean of the gradients of all of the phi i's, which means that in every step I need n gradient evaluations. Okay, so if I do machine learning and I have 35 million data sets and I need to do 35 million backpropagations at every step, I will not be finished anytime soon training my neural network. Okay, so that's too expensive. What is nice about this though is I get convergence under fairly small assumptions. I need convexity, which I never have in machine learning, but at least only convexity or kind of convexity and the minimizer exists is what I need. That's not a lot. And the step size, eta k just has to be sufficiently small, which means like 2 divided by less than 2 divided by L, where L is Lipschitz constant of phi bar, the gradient of phi bar. Or phi bar, doesn't matter. Okay, so that's a cool algorithm, but it's too hard to use. So the idea of stochastic gradient descent is instead of doing a step with respect to the actual full gradient, I just pick one of the data sets and do a step in that direction. Okay, or could also be a few. Yeah, do a batch. I never write down a batch, but you could also think of that here. It doesn't really matter for this particular problem. And this is what I call subsampling, because I have only one or a few data sets at a time that I pick. Here convergence gets a bit tougher. So I need all of these phi i's to be strongly convex, and I need this also so-called learning rate. Yeah, so what was called step size before is called learning rate now. Eta k will actually go to 0 as k goes to infinity. It's very annoying. Popular is though, and this is this implicit regularization bit that I've explained badly before. Popular is to actually have these phi's non-convex, yeah, because okay, that's what people work with, and actually leaving eta k constant. In that case, there's not actually a chance to converge to a point. I mean, okay, there's a chance, but not an actual chance. And what we will see later is that in this case, we actually have a chance to converge to a stationary distribution. Yeah, because we do something noisy the entire time. So we don't really converge to a point unless, I mean, okay, if all these phi i's are identical, then okay, that will be, but that's not an interesting setting. But otherwise, we will converge to a stationary distribution. And this stationary distribution may give you something that people call implicit regularization, and that is something people like to do in machine learning. Okay, how do we get now to continuous time? So if we just have the method from Cauchy, just gradient descent, and we let eta go to 0, or we just look at the dynamic and let eta go to 0. Yeah, I mean, what we see is this is just an Euler discretization of a certain ODE, and this ODE is a so-called gradient flow. Okay, so that's just the ODE, theta dot is equal to minus the gradient of phi of theta. Now, okay, I mean, if you've never seen, okay, probably everybody has seen gradient flows before, even without knowing that things are gradient flows, because, I mean, many PDEs are actually time-dependent PDEs are actually gradient flows of certain functions, like the heat equation, the Dirichlet energy. And this is essentially what we also apply when doing machine learning or when minimizing anything. Okay, the question is now, okay, how do we get a gradient flow for SGD? Or is SGD also a gradient flow? Or how do we get SGD continuous time? And what people have been doing for quite a long time is looking at this ST. It is just, okay, if you let eta k go to 0 and you rescale the process correctly, then you can actually show that I think the moments of stochastic gradient descent converge to this stochastic differential equation that has multiplicative noise here. So this phi is like the square root of the matrix square root of products of these subsampling gradients, which is kind of an easy CLT argument. Yeah, it's not very hard to see. And then people like to analyze this gradient flow, and I've cited like a couple of works here, but there's like a couple of like certain, like I think like order of 50 more or so that work in this direction. But I think this formulation, I mean, while it's correct, I mean, this is what you get when you rescale correctly and let eta go to 0. It doesn't tell you that much about SGD actually. Because, okay, first of all, while your correlation length is large, your method actually, so stochastic gradient descent, behaves very differently from a diffusion process. You have a much slower sampling. You actually kind of follow a certain path, and then you switch the path, and then you follow a new path, and so on. Yeah, so if eta k is not super small, then you don't actually have an SDE. You have something different. First of all, especially when eta k is constant, you can then say, okay, eta k goes to 0, but in practice it really doesn't. Yeah, so it's not really clear whether an SDE is a good model. Secondly, when we say, okay, I've analyzed this SDE, and I now want to construct an algorithm from this SDE, that's actually quite difficult because this SDE doesn't contain any subsampling. Yeah, this SDE is only full sampling. Yeah, there's always phi bar plus some noise that depends on all the phi's. Okay, so it's not obvious how to now say, okay, I pick this SDE, and now I go back to an algorithm, I get an algorithm out of this that accurately represents what this SDE does. Okay, so that's not super trivial. Yeah.
Can I just
yes. Yes.
Categorically disagree with you. Very easy to simulate with subsample precisely this.
And that's stochastic gradient descent.
Not necessarily. There's lots of things you can do. You can actually get exact samples of this process up to unbiased sample. There are ways to do it. I mean, I don't want to interrupt you, but I'm just saying that there are ways.
Okay. Okay.
But please continue. I didn't want to. I'm not trying to derail you.
I'm derailed already. Okay, we should talk about this. Yeah. Okay, so what else can we do? Okay, so if we look at single steps of the stochastic gradient descent, what we see, I mean, okay, also they are Euler discretizations of certain gradient flows. Yeah, now just not with respect to phi bar, but with respect to one of the i's. And the idea is now that the step size or learning rate, as it's called in this machine learning setting, they have two different meanings. Yeah, I mean, when we think of this step from discrete Euler to continuous gradient flow, then they are just like a numerical step size. Yeah, step size of a numerical integrator. On the other hand, they describe the length of time interval between two data switches. Okay, because they tell me how long do I follow my flow before I replace the data by a new data set. And the idea is now to actually replace the discrete process with the continuous process, but still do the data switching at a slow rate. Okay, so I still have a continuous process in every step, but I still slowly replace the data, because that's kind of what SG does as well. Is you don't switch infinitely often in a small interval, but you switch slowly in intervals.
So it's a pure jump process with intensity.
That is. Spoiler alert. Yes. No, exactly. So this is actually, it's we come to that on the next slide, because now we need kind of a way to turn this discrete time ik into a continuous time ik. Yeah, so the process that chooses which data set have at which time, and for this we use a pure jump process. Okay, so we kind of get the coupling of the pure jump process and an ODE. Of course, this pure jump process, I mean, everybody is, it's a bit like a Poisson process. Yeah, just in this case, what we do is, okay, and I have like a complicated slide that explains the exact setting, but essentially what we do is we wait in a certain position, we wait for a random waiting time, and we jump to one other point in the data set. In this case, we just pick uniformly, but much more general things are also possible. You could also say, kind of in the follow-up work, we even did, okay, what if the index is continuous? And then you can even have a diffusion process, picking the data points. Yeah. It's not state dependent, but depending on what you want to do, it might be time dependent. So because so because you either want to have this constant learning rate setting, where you say, okay, it should not be dependent, it should just be homogeneous, this jump process. It doesn't change over time at all. Okay, you still get random waiting times, but the step size essentially is a homogeneous process. Or you say you actually want them to go to 0 over time, because that is what you do when you decrease the learning rate over time, and where you actually get a chance of converging to the minimizer of your target function. Okay, so both settings are kind of interesting in their own right. And then you can just define those. Yeah, so phi is the theta is the version with a fixed learning rate. Yeah, so their process I is homogeneous in time. So here the waiting times would just be exponential. And in the second setting, we have psi, and we have learning rates that go to 0. Yeah, so the intensity goes to infinity as t goes to infinity. okay, and this is how it looks like. Yeah, I mean, you have this ODE here that sort of stops whenever I jump and starts again at the point where I left. And this, of course, is kind of like a wrong-ish setting because here we wait like way too long. Yeah, so these flows, they all kind of converge to their stationary point before I switch. Yeah, so kind of what happens here would not be very interesting. But of course, the actual idea is to switch fast enough such that you sort of kind of average between all of these processes kind of over time. Yeah. Okay. So now, okay, there's two interesting limiting behaviors. So there's the question: what happens if I have a homogeneous learning rate? Yeah. So what happens? So a constant learning rate. Then let eta go to 0. Because there I would hope that I actually approximate with my process the correct gradient flow, which we actually do. So on the next slide. The other question is, I mean, we're still optimizing. So what happens as t goes to infinity? And there, okay, we will see that for a constant learning rate, we will converge to a stationary distribution as t goes to infinity under convexity assumptions. And for decreasing learning rate under convexity assumptions, we converge to the minimizer, actually. And this actually, and okay, having told you all of this, I don't actually need these slides, but this are the formal results. So we need now more smoothness in phi I for this homogeneous result. Yeah, so this is this result that I actually have a plot here. Yeah, that when I approximate this green line, which is here the gradient flow, uniformly in time, with this process, and I get convergence when I let the intensity go to infinity or the wait time go to 0 over time, uniformly in time. Which, by the way, SGLD does as well. Yeah, so stochastic gradient descent also is a method to approximate ODEs in a sense of gradient flows. And then, okay, for long-term behavior, we will measure things in this Wasserstein distance. Here it's kind of Wasserstein distance with a distance that is kept at 1. If we need strong convexity, at least for the okay, I write down here, it's kind of strongly, they are all strongly convex. For the constant learning rate result, actually only some of them need to be strongly convex. But therefore, constant learning rate, we see, okay, there's a unique stationary measure in this case, and we converge to it at exponential speed. Yeah, so that's really fast. So the thing is, I mean, okay, kind of we can relax these assumptions quite a lot by replacing convexity assumptions by Hermann bracket conditions. Yeah, just making something that is not as strong and not as technical by something that's very, very technical and much stronger. So that's absolutely possible. We can kind of, for this result, we can use previous results. So this is not like super new. But what we see is, I mean, okay, it at least indicates that SGLD in the setting where we have a constant learning rate, I mean, I get to a state where nothing happens anymore, actually rather quickly. Yeah, which is probably good to know. But also, okay, in continuous time, it's rather quickly. When I go to, when I now want to know what actually is this thing I converge to, that seems to be very tricky to see. Yeah, so I have here some examples that are just simulated. Yeah, so these orange curves are from the stochastic gradient process. The gray curves in the background are SGLD. Yeah, so this seems to match quite closely. But this is not Gaussian or anything. Yeah, so this is actually on the fixed interval. These are defined on fixed intervals, and they have weird dimensionality very often. Yeah, so if you think, okay, you're in 2D space and you have 2 data sets, then what this process will do is actually it will converge to a line in between these two. We'll just go back and forth. Okay, depending on the if everything is linear at least, we'll just go back and forth between these two. Yeah, so you don't get a measure on the full space, the full 2D space. You just get a distribution kind of on this line in between the two. Okay, which probably makes sense, but kind of makes analysis or makes kind of showing convergence to Gaussians or something that people may want to do very tough. Yeah, unless you have some chaos conditions or you have a lot of data sets and you assume that it's always spanning the whole space, but it's not very realistic. You want to ask a question? No? Okay.
You answered it.
Oh, okay. Okay.
There, so
okay.
I
Yeah. So if we decrease the learning rate over time, we do see convergence to the minimizer, which is great. We don't get a rate though, so the rate is gone. And this seems to have to do with the setting of, I mean, these are all so-called PDMPs, piecewise deterministic Markov processes. The analysis with exploding underlying jump processes has not been very far. So there's a lot to do. But as far as I know, for the diffusion SG model, it's also very hard to actually talk about a convergence rate as eta goes to 0. So also that seems to not be super well explored. So yeah, we can keep our jobs. There's lots to do. That's perfect. Okay, and there, I did some experiments, and these are kind of in continuous time. I mean, these are two top figures, and I mean, and there we see sometimes, I mean, this is more like a rational convergence on the left side, like an exponential-ish convergence on the right-hand side, but yeah, I mean, I wouldn't. It's very hard to claim something from these pictures. Also, it's really just in continuous time. Yeah, so obviously, probably here there are many more steps than you did in this picture, like completely, just because you need to sample much more in this particular setting. Yeah, so it's not really clear how this would ever translate to discrete time. Yeah, because obviously when you make the steps much smaller, they need more of them in continuous time, and then you don't see this in the plot though. Yeah, so it's a bit.
Again, what was the difference? Because you were talking about constant rate and then the rate that was decreasing.
Jonas, can you repeat the question for the microphone?
Yeah. So I mean, okay. Your question was what was the so the difference? So what is the difference between the two plots in the top? So we have different learning rate functions. Yeah. So the way that we let the learning rate go to 0 over time is a rational function in the left plot and an exponential function in the right plot. And
any particular motivation of why you choose one or the other?
So I mean, because I mean, we were hoping. So for the rational function, I mean, we were hoping that we get a fast convergence already, although the steps decrease rather slowly. For the exponential, okay, then we didn't see that for the rational one, so then we tried the exponential one instead, and there we see, like in continuous time, we see exponential behavior. I mean, it is a straight line, but like purely computationally, getting the line on the right-hand side was much more expensive than the line on the left-hand side. Yeah, just because due to the exponential decrement of the step size, I need many more steps when t gets larger.
Yeah, because I was like kind of understanding in the standard discrete case, right? I mean, there are these conditions for the step size.
Yeah, this doesn't translate for
anyway, and we don't expect to be the continuous version of that, right?
That is true, but it works a bit differently here, because when you have exponential, it's a weird effect, because the way this exponential is it's like in time. Mm-hmm. So you sum up these random waiting times, and they get smaller, and therefore you don't really get exponential in the end. Yeah, so I've not figured out how actually kind of the sequence of these step sizes of these steps actually converges to 0, but I think actually it's slower than exponential.
Yes, but the question is whether it fulfills this convergence condition.
Yeah, I would need to look that up.
Yeah.
But I mean, the convergence condition, I mean, is always okay. It has to be like I think in little L2, but not in little L1. Exactly. I think that's the
sum of the things
of the square. Yeah, exactly. But so the thing that the sum of them is infinite is here always true. So I did prove that, because otherwise the process is not defined until infinity. That would be a problem. So this is always true here. And their squares might probably be fine. Might be. So I think this might be correct. But also we don't have an Euler discretization in between. Yeah. So the theory is probably different, anyways. But yeah.
Thank you.
Okay. And then I'm not sure what the time says. Oh dear. Okay, I just do longer than there's less time for questions.
Yeah.
Okay, but let's look quickly at sampling. So I want to still want to sample this pi given as pi as a density proportional to e to the minus pi bar. And very basically, this is just kind of basic MCMC, but very basically, it's hard to generate samples, especially if X is high dimensional. Yeah, so we cannot really use inverse CDFs. We probably cannot even compute the normality constant of this beast. So what we do instead in Markov chain Monte Carlo is we generate an ergodic Markov chain, discrete in time, that has station distribution pi, and then due to ergodicity, we can actually use samples over time to approximate integrals over space. Okay, so far so easy. There's many algorithms to actually do so, and in this setting we will look at Langevin-based methods. And there the idea is essentially to, in this case, look at the overdamped Langevin equation, and underdamped works as well, but we do only overdamped now. Look at the overdamped Langevin equation of this potential phi bar. Under some assumptions, this actually has the discretisation distribution, and is also ergodic. Now, unfortunately, when I discretize this process, so I say I do Euler Maruyama, then I don't necessarily retain the correct station distribution. So I get maybe close to it, but not the correct distribution. So I can do one of two things. I can either metropolize and converge. It's called MALA, metropolis adjusted Langevin algorithm. Or I make an error and I don't worry about it. Kind of both is possible. And it is very kind of which one of the two you choose. If you ask like 5 statisticians, they will probably give you at least 4 answers. It's a very fundamental, very philosophical question as well, because I mean, of course, MALA does converge as t goes to infinity, but maybe you cannot actually get there because it's more expensive. It's a difficult problem. But for now, for this talk, we will actually look at Euler. This is how it looks like. So this actually is accurately approximated because it's just Ornstein-Uhlenbeck. So I can actually get the correct sample path. And we see that all of these samples seem to approximate with this histogram the correct density. Okay, so this is like just subsample idea from Stochastic Gradient Descent, where it seems to work quite well. It doesn't really work in Markov chain Monte Carlo. Accurate algorithms are difficult to use. I just said this in the beginning already. And approximate algorithms are not always great. So we anyways here look at an approximate algorithm and try to figure out whether, they're great in continuous time, and we'll see whether that works or not. This sort of approximate algorithm is called Stochastic Gradient Langevin Dynamics. And this is just what happens when I combine the Euler idea from before with Stochastic Gradient Descent. So this is just essentially, so Euler was like using phi bar here in an Euler Maruyama discretization of this SVE. And now I just use a phi I that I subsample. Okay, so same idea as before, just plus some noise. Error analysis shows okay, but not great. Okay, what does that mean? So this result actually is actually fairly nice. I had a result here before when I gave this talk last time, a couple of weeks ago. That was much worse than this, and that I thought was the latest result. But then somebody in the audience told me, no, we actually have a better result. So welcome to my life. But here at least what we still see, and the last result didn't even converge. So here it does converge, but what we see is we have a very strong dependence on the dimension of the problem. So here it's exponential dimension. So this is kind of the bit, the sort of ergodicity bit. So that goes down as k goes to infinity. K being the time step. And I kind of have this like bias that is introduced by the subsampling over here. Here just see, if the dimension goes up, then it may converge very slow, or in infinite dimensions won't work at all. And it's linear in the dimension, the bias linear in the dimension. This is much better than the result I had here previously. but there's still a very strong dimension dependence. That let's see whether we can get rid of that in a continuous time setting. Okay, so I mean, what comes now is probably exactly what you've expected. So we look at this at the Langevin SDE from before, but now we combine this idea with this continuous subsampling from before. Yeah, so you get a regime switching diffusion process, I think is what professionals would call it, where this index process I is just given as before or slightly differently. Yeah, so it's actually fairly open. Okay, and how does it look like? So here what we do is we try to approximate the Plough distribution, which is kind of some Gaussian, and we now try to use two different, so we say, okay, we're given two different data sets between which we switch, which are also Gaussian, so it's all just Ornstein-Uhlenbeck processes. It's all continuous computations, yeah, so it's all accurate sampling. And here we see, okay, this is pretty bad. But here also, we kind of switch very slowly. Yeah, so I kind of color coded when we approximate which distribution. Yeah, so when this is black, we sample from that distribution. When it's green or probably teal, sample from the bottom distribution. And if we switch very slowly, then okay, we get this kind of bimodal thing. It doesn't have any mass in the Plough area, which is probably a bad sign. But if we let what? Sorry.
Again, the blue.
So the Plough is the target distribution. So that's what you want to sample from. That's also Gaussian. And so it's kind of, it's like some Gaussian. I mean, yeah, I mean, it's actually this Gaussian. And I kind of construct this Gaussian by doing some completing the squares type thing to get this Gaussian. So this is a sum of two Gaussians of two data sets that are both Gaussian. And I now try to very sillily approximate this Gaussian using this data subsampling. So in this particular case, we wait really long. Yeah? So the wait time is very long between two switches, which obviously wouldn't work. Yeah, so you need to be much quicker at going back and forth. And so here we are a bit quicker. Yeah, so here we still spend a lot of time with the single data sets, but at least we see that, okay, there's a bit of mass in the Plough area now, but we're still kind of weirdly bimodal, so that's still not great. But if we get much quicker, then we actually see convergence to the Plough distribution. But we have to be really, really fast. Okay. So I say this is a somewhat unrealistic example. That's kind of the title, because of course you would usually hope that data sets are not completely excluding each other. Yeah, so we'd usually hope that the green bit and the black bit are fairly overlapping and are fairly close to each other. And that might also be why you do like a batch subsampling, where you say, okay, you don't take one data set at a time, but like 100 or so, or like 1,000. And then you have a chance of actually these already looking much closer, but it's not, but you don't see as much, like you don't get as much of a fun picture here. Okay. So, I mean, what we've seen in the example is though that, I mean, we still see some kind of stationarity, I would say, also in these distributions. Yeah, it's just stationary with respect to like a weird distribution, but it's still stationary. Yeah, so there seems to be some ergodic effect happening. And the other thing that we see is when the learning rate is short, we actually seem to converge to the correct thing. Yeah, so when we switch really, really often, then we seem to actually approximate the correct distribution. Yeah, because this, I mean, has worked here. Yeah. Okay. So what we now want to do is, okay, we want to show ergodicity and speed of convergence of the subsample processes. We want to look at the error between the stationary measure of the subsample process and the actual distribution, and then kind of get a bound similar as before, where we say, okay, what is distance between stationary measure and our process using triangle inequality. Okay, so we need some assumptions. I mean, okay, we need some Lipschitz assumption just for these SDEs to be well defined, and we need some kind of convexity outside of a ball, which is a bit more than what the other people have. They have only dissipativeness, which is a bit weaker than this, but it's not convexity. Yeah, it's just convexity from you look from afar. Yeah, so kind of as values get big, you don't explode or anything. Yeah, so it's just kind of preventing you from that. but it's just convexity when you look from afar. Yeah, that's what I just said. And then, okay, what we see for ergodicity is there's a unique distribution, mu eta, and we converge this unique distribution at an exponential speed. And neither prefactor nor rate depend on the dimension of the problem. Yeah, which I think is nice. Secondly, what we get for the stationary distribution is, under these assumptions, is the distance of the subsum distribution and the actual distribution is small, measured in the waiting time eta. Yeah, so this is very cryptic. So this like C phi here is about 1/4, a bit more, a bit less than 1/4.
But this positive.
At least it's positive. Yeah, exactly. So this converges very slowly as eta goes to 0. Yeah, or as rate goes to infinity.
And it doesn't discriminate.
It's oh yeah, sorry. So the prefactor depends square root of the
exponent.
The exponent. No, the exponent does not. Yeah. Okay, but at least it's not exponential in dimension. Yeah.
Yes, exactly.
Yeah. Okay, and then when we do triangular inequality, okay, we just get a sum of the two previous results. And okay, we see, okay, there's no bias diverging, okay, which happened in the 2017 result. And dimension dependence actually only in this prefactor, yeah, and only square root. Yeah, so not exponential. Okay, but of course not a real algorithm. Yeah, so we can be excited, but not too excited, because we still need to discretize this in a better way to get a real algorithm and get a better methodology. Okay, I don't really have conclusions. I only have kind of like what have we done otherwise and where we go from here. But maybe whilst we are kind of staring at this, there could be time for some questions.